Hello, everyone. I'm Mason. I work at Scroll, and so I help write the ZK circuits there for the zkevm we're building. And today I'm going to be talking about building and testing circuits with Halo2 Community Edition. Okay, so yeah, sorry. Okay, so yeah, just an overview of what the slides are going to be. So talk about what is Halo2. Go through an example Fibonacci circuit, and then we're going to talk about the actual hackathon goals, which are these Ethereum precompile hash functions. And then there's another example, and then we're going to take a look at the GitHub repo that we built that has the framework and the examples in it. Okay, so what is Halo2? So Halo2 is a Plonk-based proving system. And so what that means is, you basically have this circuit that consists of basically this giant rectangular matrix of witness elements that, and a set of constraints that sort of says that sort of defines polynomial relationships between elements in this matrix. So in particular, we generally think of the matrix as having rows and columns. And so it has 2 to the k rows, where k is sort of this degree, and then m columns, and m sort of can just be any number that you want. And we are going to fill this out with elements from a finite field f sub p. And then and then write down constraints between these elements. So for each column, we're going to end up constructing this Lagrange polynomial that interpolates the values in each column, right? So this ai sub x will pass through at the first root of unity, right? So at the first root of unity, ai sub x will evaluate to whatever field element is here, and then so on and so on. And then basically what Halo2 is going to do afterwards is once you've written down all these constraints, there's a way to combine all these polynomials into one, and then we're going to prove something about the resulting polynomial. So in Halo2, there are these different types of columns, and so there's these advice columns and instance columns, fixed columns, and selector columns. And so advice columns are sort of I think of as private inputs or witness values. So these are things that the prover can see, but the verifier sort of knows nothing about if you're doing this in a ZK context. And then the instance columns are I think what people call the public inputs. So sort of this is values that the prover and the verifier can see. And then the fixed columns are so these sort of have values that the prover and verifier agree upon at the beginning of the setup. And then the selector columns are sort of just they're sort of a special name for fixed columns that we agree that they only have 0 and 1 values in them. Okay, so yeah, so the one key difference between advice columns and instant columns versus fixed columns and selectors is that the advice columns can vary between proofs. The advice columns and instance columns vary between proofs, while the fixed columns and selector columns cannot. So if you want to change a value in the fixed column or the selector column, then this requires you sort of have to redo the circuit setup. So this means that there's going to be a new verifying key and proving key that corresponds to the sort of the different fixed column and selector column. Okay, and then so the big thing with the big thing that we use with in Halo2 is sort of these custom gates, which sort of let you write polynomial constraints between cells. And so the general layout of a custom gate is sort of each custom gate sort of has a selector that controls whether or not it's enabled or not. And then it can sort of make reference to sort of any configuration of advice columns, instance columns, and fixed columns. And so, and then in this, you sort of you use relative offsets to say okay, right? So this column, right, is at a relative offset of it's like A2 and an offset of 0, like relative to this selector value here. This is A3 at an offset of 0, A4 at an offset of 0. This cell, right, is an A3 at an offset of 1, and A4 at an offset of 1. Yeah. Okay, and then so like the cells in a custom gate don't need to be contiguous, right? So you're allowed to have like one custom gate that references like A1, A0, A1, and A3, and like I1. So even though like the way that the circuit has been laid out, these things aren't touching, like this is not a problem in Halo 2. Okay, and then so another big thing in Halo 2 is something called an permutation or equality check. And so what this does is it allows you to assert that like various cells are in fact have the same value. So like right, so like in this case, right, like so like I can say that like okay, A1, the value in A1 and A3 is the same, or like the values in A2, A4, and A1 or in I1 are the same. And so the reason this is called a permutation check is because how do you actually prove this is you construct like a permutation that has these cycles in it, and then you prove like this like permutation polynomial. You prove something about like this permutation polynomial. And so in contrast to fixed custom gates in Halo 2, like the offsets here are actually absolute. So like you can sort of reference like this cell, which is like the fourth cell like in A1 is equal to the second cell in A3, and so on and so on. And so generally what this is used for in Halo 2 is like you write gadgets that sort of like prove like smaller facts about like field elements, right? So like you might prove that like, okay, like, A1 plus A2 is equal to A3 here. And then like you might want to like link this A3 value here with the input of some other gadget, like somewhere else in your table. And to do that, you could use like a permutation check. Okay, and then the sort of like the final big tool in Halo 2 is something called like a lookup argument. And so what this does is it basically allows you to check that, say like this tuple A3, A4 is in one of the values in this like set of columns like F0 and F1, right? So here, like, maybe like I've written like 1, 1 here, or let's say like, something like slightly like more like interesting, which is like, let's say like F0 and F1 sort of have like F0 has all the all the 256, all the values from like 0 to 255. And then F1 has like the values, like sort of like the binary knot of all those values. And then in A3 and A4, like I want to check that like, that relationship, like that A3 is in fact like, the binary knot of A4. And so to prove that, I can just do a lookup argument. And so this is a lot faster than actually writing down all the constraints that you would need to check that, a 256-bit value and another 256-bit value have this binary knot relationship. And so like one big difference in Halo 2 versus Halo 2 CE is that in Halo 2 CE, you can actually do lookups between like say 2 advice columns. Whereas in Halo 2, you can only like the lookup for the advice column has to be has to be fixed columns. And so in Scroll's zkevm, we basically use lookups everywhere to link different subcircuits together. Okay. And so, sorry, this is just like an overview, like sort of in words about like what Halo 2 is. Right? So we have both custom gates and lookups, and then it's very flexible for like different circuit constraints. And then like one thing I didn't really cover here, but is that like Halo 2 is modular enough so that you can sort of replace the backend. So like in Halo 2 CE, we've actually added KZG commitments instead of like Halo 2, which only uses like an inner product argument. Okay, so that's just sort of like an overview of what Halo 2 is. Now we're going to actually talk about like how you would actually use Halo 2 to like code up a circuit. So the if you'll remember the circuits, the columns I talked about earlier like actually correspond to sort of like this like advice column, instance column, and fixed column, and then selector. All right. And selector and table column are sort of just like aliases for, I believe, selector is just a fixed, actually selector and table column are both just aliases for a column with type fixed. And so, yeah, so like a selector, right, just holds binary constants, right, so 0 or 1. And so it's being used to tell, to control whether or not like constraints are enabled or not. And then a fixed column is just what halo2 uses to tell the compiler that like, oh, this column is going to be used for lookups. Okay.
Can I ask you a question real quick?
Oh, yeah.
We've got someone from the audience asking, are gadgets subsets of gates or just a set of constraints for the gates?
I believe typically it's sort of like vague and amorphous, but I think I typically think of like a gadget as sort of like it's like a bunch of constraints and then sort of it's a collection of the constraints and like the columns that like the constraints sort of like reference. Yeah, so I guess like I view like gadgets as living like sort of above custom gates. Did that answer the question? I don't know who asked it.
Imdroid did and says makes sense.
Okay, cool.
Thanks.
Great. Okay, yeah. So and then like how you would actually create the column in halo2 is there is this, I believe this is a crate in Rust. And so called the constraint system, and it basically has this like a bunch of like methods that you're required to implement. And so like one is like advice column, which basically tells the constraint system like, hey, like I want a new advice column, fixed column and instance columns, and then selectors, right? And so all of these basically just tell the constraint systems like, you know, increment a counter somewhere and like give me a reference to like an index for one of these. And then okay, so then like what do you do with the columns once you have them? So like one thing is like, okay, like if I want to enable this you know, equality or permutation check on the columns, then I have to tell the constraint system like, okay, you should enable equality on these, right? Because the default is like equality checks are not enabled on a column. And then if you enable them, then this means that like, you know, as part of proving, you have to do a bit of extra work to include this in the permutation polynomial. Okay. And then so like this is sort of the signature for running a custom gate. Let's see. So basically what this does, right, is like self here is the constraint system. Name is just a string that basically tells the constraint system like this is sort of like a label for it. The label will be printed if you sort of like assign your constraint system, if you assign your proof like incorrectly, then it'll like the prover will be like, hey, like, you know, you failed to satisfy this constraint, and here's the name that you like gave it. And then so like the actual part of the like the actual important thing in here is like sort of the constraints, right? So this is a closure that basically takes these things called virtual cells and returns an iterator of C, where C is, let's see, C. Okay, well, yeah, so C is this thing that can be like sort of into constraint, which basically means in this case, like there are like, it's a function, right, that takes sort of like a bunch of like columns, and it sort of like maps them into polynomial like relationships between the columns. And so I think this will be more clear once you see like what you actually call a create gate with. Okay, and then finally, to add a lookup argument, so we have this method called lookup any, and so again, there's like self, which is the constraint system, name, which is the like the name of the lookup, and then this table map, which is again a closure from a map of like, which is a closure from like a bunch of columns to a vector of like expressions. And so the expressions are sort of like are sort of these polynomial relationships between the columns again. And so this is like a vector of tuples of expressions, because like I think the first one is like basically you want to say like, okay, like the first one is like somewhere in the second one. Okay. So again, I think this is more clear, like once you actually see like what the, like how this is used. Okay, so how to like actually implement a circuit in Halo 2. So first you have this struct, which is typically called the config, which basically just holds all the columns that the circuit uses, or like say the gadget that the gadget uses. And then you define a chip struct that sort of configures constraints. And so you call basically, the constraint system dot custom gate for like each one of the custom gates that you want to add here. And then also in the chip struct, you typically define the method that sort of like does the assignment into the table. And so this is, okay, so I guess first I should mention that there's sort of like two phases, right? In Halo 2, right? One is like you're configuring the circuit, which is sort of like you're listing all the constraints. And then there's like the assignment or synthesize method, in which you like assign like field elements to the tables. And then so yeah, the chip struct typically implements both of these and something called like a configure, and then another method called either assign or like synthesize. And then you define a circuit struct that implements the circuit trait. And so I will go over what the circuit trait is later. And then you can instantiate a circuit instance and feed it into the prover, which will actually generate like sort of the ZKP, or the mock prover, which will sort of do the which would sort of take like the assignments and check that like one by one that these in fact all match your the custom gates or constraints that you've written. And so the nice thing about using the mock prover, right, is that like if you feed it into like the real prover, then all the verifier can do is just say like this like passes or it doesn't. Whereas if you feed into the mock prover, then it can actually tell you like, okay, like, this is the one particular custom gate that you didn't satisfy.
Mason, two questions real quick, if that's okay.
Yeah.
One is, so the lookup _ any, is that one of the main differences, or one of the differences between Halo 2 and halo2-ce?
I think, yes, that's I think in my mind, at least that's like the biggest difference between Halo 2 and halo2-ce. And it's, like basically a lot of stuff that Scroll has built for the zkevm like is not doable with fixed lookup columns. And I can talk more about that later when there's a slide about the zkevm architecture.
Cool. And then the other question is the chip like the proto board of libsnark?
I don't quite know what the proto board of libsnark is. So yeah, I guess I don't really know. I can't really answer that question.
Awesome.
Yeah, I think like the chip struct is like, you're sort of like, it's pretty flexible in like how you want it to be. Like there's no like, in the Halo 2 examples, they have some, I think they have something in their mind where like each chip like contains a config, but also sort of like implements like whatever function that you wanted the chip to prove. But then sometimes like I think it doesn't make sense to have this chip struct. Sometimes it does. It all depends on what your like architecture is. Yeah, I think it's like it's easier to talk about like sort of like in concrete terms rather than like sort of like abstractly. So yeah, I don't know. Hopefully that made something clear.
Cool. Thank you.
All right. Okay, so yeah, the circuit trait as promised. Basically, this is something that Halo 2 wants from you. And so basically to feed something to the mock prover, it has to implement the circuit trait. And this has a couple of types with it. So the one that you like probably care about is the config, which is sort of like, here are all the columns that the circuit is going to use. The floor planner is not as important, I guess. And so basically like a big thing that Halo 2 sort of does in the back end that typically you don't have to worry about is sort of like, how do you pack all these like columns and like custom gates together? Because, right, so like it can sort of see like, oh, like sometimes, this selector is only enabled like for these offsets and not enabled for these other ones. Like maybe like you can pack like the cells like together more efficiently. And then this is great, right? Because now your table is like smaller in size. But typically we just use something called the simple floor planner, which doesn't do too many optimizations, and it's fine for like certainly running like a small circuit. But then, you know, if you want, like, if you have like a really like complicated or like expensive circuit in mind, then like it might make sense for you to like implement your own floor planner. Okay, and then so let's see. So then there's this function called without witnesses, which generally is just like, you know, it's just like sort of like the default value of the circuit. And typically what this means is that like you're not trying to prove anything with the circuit. Like the halo2 actually just calls this, I think, to figure out like how what offsets and columns does this circuit actually use. And so that's used to like figure out like sort of like what's the maximum offset and things like that. And then to configure here is the like sort of what I mentioned earlier, right? And so this is like you're given this constraint system, it's typically called meta, and then you have to return a config, and then like the actual work that you do in this function is sort of like you write out all the constraints that you want your columns to satisfy are written here. And so like again, I'll show like multiple examples of this later, and so it should become more clear. And then to synthesize is sort of like the assignment function, right? And basically what it does is like you get passed back the config, and then what you do here is you use the witness values that your circuit has access to now to fill out the trace table. Okay. Okay, so just have something to talk about. So here's like you know, everyone's favorite Fibonacci circuit in halo2, and so right, so just like right, just in case you forgot, right, like you want to prove that like you know given like this like recurrence relation, right, that like a2 is equal to a0 plus a1, you know, given two sort of like arbitrary starting values, we want to prove that say like, you know, f9 is equal to z for some like public input z. And I guess x and y are also going to be public. Actually, wait, sorry, no, so I take that back. X and y are just advice columns here. Okay, so let's see. So like the actual like layout of the trace table will look like this, right? So in this case, right, we started with like the actual Fibonacci number. So like f of 0 is 1, f of 1 is 1, right? And so you get 1, 1, 2, 3, 5, and so on and so on. Then we're proving that I guess some value in like the ninth value, say, is 55. Right. So how would you do this with the with the custom gates we talked about? So first, I guess, right, like given this like trace table that we have here, the config can consist of 3 advice columns, 1 selector column, and 1 instance column. Right. And so in the configure function, we're going to have to, you know, do like, okay, well, like columns A, B, and C are all advice columns. So we just tell the constraint system, like, you know, give us 3 advice columns, 1 selector column, and then 1 instance column. And then here in the ... we actually have to write the constraints that like we want to hold between these 5 columns. And then finally we return the config, right, which is just the columns themselves. So like, yeah, so let's go over like what actually happens in this ... part. Right, so the constraint that we want, right, is that right, like I think it's like A plus B, column A, the value in column A plus the value in column B is equal to the value in column C, right? And then of course, right, we only want this to hold when the selector is enabled. And so, right, so here, like in Rust, we would write out, right, like so S is equal to meta.query selector. And so this query selector and query advice, right, is basically just telling the constraint system, like, hey, I want the Lagrange polynomial that corresponds to this. Right, so you get the 3, and then you write out like, you know, S times A plus B minus C. And so the implicit like thing here is like, actually you want this to equal 0. And so like, if you want to have multiple constraints, then you just sort of like add more elements, elements to this vector. Right, so the actual polynomial constraint that we want to hold here, right, is that S of x times A of x plus B of x minus C of x is 0. Okay, and then, right, but we're not done yet, right? Because like now we've written sort of like the constraint, right, that holds between A, B, and C at like the offset 0. but we need some way of linking like the rows in this, the individual rows in this matrix together. And to do that, like we use an equality check. So we have to first enable equality on A, B, C, and instance, right? So, right, because the equality checks that we actually want to do, right, are that, you know, that like to go from like row 1 to row 2, you want to copy this value from B into this value in A, and this value, this cell in C into this cell in B. And then we also want to verify, right, that in fact, like 55 from our instance column is in fact like is like this 7th value in C. And so, oh, sorry. Okay, and then so in the configure function, you would do these equality checks, and then so the actual individual equality checks are actually get added in the synthesize function, where you do like cell A dot copy advice. So you're copying A to B, and so you're saying like basically for cell A, I want to copy the value of column B at the offset -1. Right. And so this is sort of like the one exception to like the rule I stated above, where, you know, in the configure function, you add the constraints, and in the synthesize function, you do the assignment. Here, like you're in the synthesize function, but actually you're doing both. You're both adding the constraint and doing the assignment. So this copy advice does two things. And then so here again, you'd also want this like cell B copy advice, and so to copy like B to C, like C to B or B to C. Okay. But then, okay, so like that was one way of doing the Fibonacci numbers, but like you might say like, oh, like, you know, I can like get rid of some columns, right? Like why have all this like copying of like numbers like around when like I could just, you know, have like one column, right, with the Fibonacci numbers in it, and then just write down the constraints that have to hold here. And so like, yeah, if you do that, then you'll end up with this config that only has 3 columns, right? So this A, this one advice column, one selector column, and the one instance column. And so here, so here, right, we want to write down sort of this polynomial identity, right, which is that like the first 2 values sum to the 3rd value here. Right. So here we do like A is equal to meta.query advice at this rotation, which is current, and then B, which is meta.query advice at the rotation next, which basically is just shorthand for like at an offset equal to 1, and then C is equal to meta.query advice at a rotation 2, which is sort of like you've rotated the polynomial by like omega squared. So now you're at this now you're at row 2, and then again it's actually the same constraint as before, right? You just have like the selector times like A plus B minus C. So it's sort of like, so the polynomial identity, like even though the rest is like the same, like the polynomial identity that we've written here is actually different, right? Like it's A of X plus A of omega X minus A of omega squared, but times X. And then that times the selector is 0. And so like, but the benefit here, right, is like now I don't have to enable the equality checks, and like I've saved 2 advice columns. Okay. So no, we can talk just, I guess, about sort of the like the hackathon things, which are not Fibonacci numbers, but instead these things called Ethereum precompiles, which are contracts that are sort of like pre-deployed at fixed addresses in Ethereum. And the ones that we care about for this hackathon all do like hashing of various types. And so basically like all of them sort of just, they're deployed at these like relatively like low like address numbers. And then they just, so I guess the first one, right, is just like SHA-256. This is a hash function with 256-bit output. And it's used I think the reason it's included as a precompile in Ethereum is that it's using the Bitcoin's proof of work. And so the idea here is that if you have this as a precompile, then there's an easy way to sort of like check things, like validate like block headers, Bitcoin block headers. And then, so then again, there's this also Bitcoin related is this thing called RIP-EMD 160, and this is used for creating Bitcoin addresses. And then the final one is Blake2F, which is added after like sort of like the initial Ethereum specifications, and it's used for like Zcash proof of work. So I think for all of these, like it's more helpful for like you to just like, rather than have me talk about them, just to like look up the specifications in the GitHub repo that we have, or like on Wikipedia, because yeah, honestly, I'm not like an expert on like how any of these functions work. Okay, but like the goal of the hackathon, right, is to write like a circuit, right, that will verify that, you know, like we'll verify that, like, you know, for a sequence of bytes, then like say the SHA-256 of these bytes is like the claimed value. Okay. Okay, and then so like the reason that like we want these in separate circuits for the zkevm is like sort of like has to do with like the architecture that we have for the whole zkevm, right? And so it's sort of basically just like lookups everywhere is how the individual circuits are linked together. So at the very top we have this like EVM circuit that verifies sort of like basic like sort of like operations in the like EVM. So sort of like here's like, you know, the gas left, here's the stack pointer, here's sort of like the maximum memory size, here's like, you know, the address that like I'm executing the bytecode for, and so on and so on. But then, right, there's a lot of like additional things that you will need to like verify like sort of like the EVM correctness, right? So so like just like as an example, like one might be like, you know, that the bytecode table, right? So this is going to sort of verify that, you know, like so in the EVM circuit, like all you have access to is sort of like the current opcode and the sort of like the code hash for the opcodes for like sort of the account that you're in. And so the bytecode table actually verifies that, you know, this like sequence of opcodes and then passing into the EVM circuit corresponds to the bytecode. Corresponds to the code hash of the claimed code hash that the EVM is using. Right. And then the way that the EVM circuit actually like the way that like the interaction between these two is actually done through like one lookup. Right. So there's something that identifies like the sequence of opcodes in the bytecode table. And then another thing that that is like sort of like here's like the code hash, and the EVM circuit just does a lookup into the bytecode table that like, hey, like this thing is there. And then so like all the other ones are sort of done the same way, right? Like the catch table does computes like SHA-3 of like a bunch of like input bytes, and then finally it produces one 256-bit digest. And so I guess like the tables, the circuits that you'd be building are actually like most similar to the, well, actually like basically are the catch table, but just for different hash functions. Okay, and then so I think, yeah, like so now I'm just gonna go over like sort of like another example that's like sort of less contrived than the Fibonacci example, but like still simple enough to go over in like half an hour. So just like sort of like quick math like trivia. Basically, if you have an element in a finite field, then some elements will have square roots and other elements will not have square roots. And then for the purposes here, we're going to call an element a quadratic residue if it has a square root, and a non-residue if it doesn't have a square root. And so, yeah, about half the elements have are residues and the other half are not. And I say about because like FP has a prime number of elements, and so like whether so like 0 is typically considered not a residue and not a non-residue, but for the purposes of this circuit, we're just going to call it a residue. So basically, like we want to write a circuit that proves this function y is equal to f of x, where y has the fun property that you know the ith bit of y is 1 if x plus I is a quadratic residue, and 0 otherwise for, you know, I in 0 to 64. So just as an example, right? So for like this particular like scalar field, for the like scalar field of BN256, right? We want to compute like, okay, like what's f of 0? And so it turns out that it's this 64-bit number that starts with a bunch of ones, and then the first 0 is in the 5th position. And so the reason this is because, you know, 0 is a square, 1 is a square, 2 is, it turns out, the square of this number. 3 is the square of this number, and 4 is the square of this number of 2. And then 5, it turns out, is not a quadratic residue. And so you can verify this using something called Euler's criterion. But then the fun fact is that, so Euler's criterion actually involves like computing a relatively large exponential in the order of the field. But it turns out that in a ZK circuit, you can actually demonstrate that an element is a non-residue pretty easily. And so we'll go over that in the GitHub. Okay, so so if you want to actually like write up the code for the Fibonacci examples yourself, you can take a look at this repo here that Haichan has, that has like there are examples 1 and 2 in the Fibonacci repo, and then I think there's 2 more examples there if you want to sort of learn like even fancier ways to write like Fibonacci circuits. And then, so then the GitHub, the repo that we're going to be working in is this thing called under the scroll tech repo called like ZK MOOC halo2. So if you go there, okay. So we go there. So here, this is the repo. And so I guess, yeah, first we will go over sort of like the examples. So here I have, so here, this is the sort of like this like quadratic residue thing that we were talking about earlier. And so, yeah, so I guess, I don't know, does anyone have any questions first before I go into the code?
Haichan has jumped in and has been helping answer some ZK questions.
Oh, okay, great, cool.
Yeah.
Okay, yeah, then I will continue. So yeah, so basically, right, like the config that we're going to use for the entire circuit consists of 1, 2, 3, 4, 5, 6, 7 columns, right? So 7 columns here, right? So there's 2 selectors, 1 index column, which is fixed, and then 4 device columns. So this like always enabled column is sort of like a gotcha, right? Which is that, right? So like, you know, in Halo2, right? Like you might think like, oh, like, why do I need this selector column, right? If I want a constraint to like always be enabled, right? Like why not just like leave out the S and be done with it? It turns out that you can't, because it's not guaranteed that like the offsets that you use like fully exhaust the trace table. And so like basically you need to have this like selector column which is always enabled. And so basically I'm always just going to assign like enable it. And then if you do this, then you avoid these things called constraint poison errors, which is what Halo2 uses to tell you that like basically every constraint needs to like basically reference a fixed column in one way or another. And so the easiest way to do that is just sort of have this like always enabled selector. And then, okay, so index is non-zero. It's more easy if I talk about index first. And so index, right, is just, right, the thing that I want to prove, right, involves sort of like the bits from 0 to 63. And so like the index here is going to be a fixed column, right, that just runs like 0, 1, 2, 3, all the way to 63, and then just repeats, right? And so the nice thing about fixed columns is I don't need to write any constraints about this. I just sort of assign whatever I want to it. And then everyone can see, because it's a fixed column, then this is public, and everyone can see that like, in fact, like I haven't lied about what I've assigned here. Then index is non-zero is a selector column, which basically is 0 if index is 0 and then 1 otherwise. And so this is right, like it's going to be 0 every 64 rows and then 1 otherwise. Okay, and then the actual device columns in the circuit are going to be value, right, which is sort of like the value that we're trying to prove f of x for, or so x in this case. All right, so what we're trying to prove f of x for, and then is residue, which is a column, an advice column that it's going to be 0 or 1. And then basically, you know, it's 1 if it's a residue and 0 if not. And then pattern, which is sort of going to be this sort of like the output that we're going to build up like sort of bit by bit over every 64 rows. And then this final advice value called square root, which is how we're actually going to prove that a particular, you know, that like value plus I like is the square root or is not is a residue or is not a residue. Okay, so first I think it makes more sense just to go over the configure function. So here, so right, so like first, right, we need to tell the constraint system, okay, like give us the columns that we're going to need. And so here, right, we get the selectors, the fixed column, and then the 4 advice columns. And then, all right, so the first one, right, is we want value to, value should like not change over the 64, like over each like 64 block of rows. And so the way we do this, right, is we write like the constraint is this one, right? So like the current value minus the previous value is 0. Right, means that in fact the current value is equal to the previous value. And then we want this to only be true on, we want this to hold for all rows where index is non-zero, right? Because the current value is allowed to change from the previous value on the first row of every 64. So index here, right, remember, just goes from 0 to 63. So in fact, index has the property that we want, that it's 0 for the first one and non-zero for the other 63. Okay, and then so right, and so like I said earlier, right, we want like is residue to be binary. So the way you get that, right, is you basically say like, okay, is residue is 0 or 1. And so if residue is 0, then then this term will be 0. If residue is 1, then this term will be 0. You multiply them together, so you get the OR of the two things. So like either residue is 0 or it's 1. And this one is always enabled, so we use that always enabled selector that I was talking about earlier. Okay, so this is where it gets more exciting. So basically, so now there's 2 cases, right? Like either is residue is 0 or is residue is 1. So if value plus index is a quadratic residue, then we want the value in the square root advice column to be the square root of value plus index. And so like, right, what does it mean for it to be a square root? Well, like, the square root squared is equal to value plus index. And so, right, so we define, let's see, so square root dot square, right, is just, you query the square root advice column at the current rotation. And then the square polynomial here is, all right, sort of like the sum of the value column plus like the fixed index column at the current rotation. And so we want this to be true, right? We want the square of the square root to equal like value plus index if is residue is 1. And so, right, so you can just multiply by is residue in this case, right? Because this is 1 if this is either 0 or 1, and right, so we're saying that like the square root is equal to the square root squared is the value plus index if residue is 1, and then if it's 0, then we don't care. Then like this constraint is always going to be true, right? And then so again, we have to throw in this always enabled selector so that we don't get this constraint poisoned error in the mock prover. Okay, and then so the more like the next one, right, is like, okay, well, how do we prove that let's say like value plus index in fact doesn't have a square root, so it's non-residue. So how do we prove that? So it turns out that this is actually almost as easy to prove as like value plus index being a quadratic residue. The way that you prove something is non-residue is like if you have if you have something that you know is a non-residue, then it turns out that sort of like this non-residue times your non-residue will have a square root, is guaranteed to have a square root. And so, all right, so as long as we can agree on as long as we can find this non-residue and agree on it, then in our circuit, we can just prove that value plus index is a non-residue by showing that non-residue times value plus index has a square root. And so that's what's like, yeah, that's what this constraint does here, right? So first, right, we need to compute this polynomial expression for is non-residue, right, which is the not of is residue, and that's like what you'd expect it to be, which is 1 minus this is residue advice, like a polynomial, and then okay, so then this non-residue we like pass in the configuration. We pass it in the configuration file, and so we just have to convert it into this constant polynomial. I think in this case we're going to. I think we use 5 as a non-residue, and then so square root and value again are like we did in this previous custom gate, and then so this yeah, so this constraint, right, it's just sort of like it's always enabled selector times this non-residue times like this expression, which sort of is going to tell you that the square root is equal to the square root squared is equal to this non-residue times this thing that we're claiming is a non-residue times the fixed non-residue. Okay. And then finally, the final constraint we need is right, like so now we have this like in every row, like is residue is like either 0 or 1 correctly. And now we're trying to build up this pattern, which is going to be the result of the sort of like the final result after 64 rows, like sort of bit by bit. And the way we do that, right, is we just right, so we're just doing, you know, this current pattern is equal to like is residue, so this is 0 or 1 times like, you know, the previous pattern shifted over by 1, so just 2 times it. Right, and so okay, so yeah, so this is that expression there, and then we also need to say like, okay, like when does this custom gate like constraint actually hold? And right, it turns out that we only want this constraint to hold every 63 out of 64 rows, right? Because on the 64th row, then we're about to sort of compute the value of a new we're about to compute the value of a new pattern, so we should start over. So actually, it turns out here that I don't know if anyone can tell me, like I think I'm actually missing a constraint in this circuit. I don't know if anyone can tell me what it is. No. Oh, so the constraint that I'm missing is actually that I think right now this current pattern, right, is constrained on 63 out of the 64 rows, but it's actually not constrained on the it's not constrained on the 64th, right? On the 64th, we actually just need that current pattern is equal to is residue, right? Or else, like, you know, I could start the current pattern at any value I want and then sort of compute like, you know, end up proving values, right, that are larger than 64 bits. Okay, so those are the constraints. Well, you know, they're all the constraints minus the one that I didn't write. And then so now we have to get to the assignment of the like how do we actually, you know, get these constraints to hold? And right, so here, right, so like so where that actually happens, right, is in this this synthesize function in the circuit, right? So you'll see, right, we just call chip.value.assign. And then, right, so this function assign is just sort of assigning, just iterating over all the values that I want to prove and sort of calling this like assign value function on each one of them in turn. And so here's like where like the work actually gets done, right? So in assign value, right, I have to go through the columns in the config and sort of tell this until the circuit's like, okay, like which value should I put here, right? So let's see. So, you know, so I guess like, yeah, I do the select first. And so, you know, always enabled is always enabled. So I'm just like always going to enable it. Index is 0. I only enable it, right, if the index is non-zero, gets enabled if the index is non-zero. And then so the final fixed column, right, is the index column, which just gets assigned to like the values like 0 through 63. And then, right, so the value column, right, is the value column, right, is just whatever value we're trying to prove over these 64 rows. And then so here, right, we actually compute like the stuff that sort of that changes row to row, which is the is residue and square root values. Right. And so here we're just computing, you know, like in Rust, like what the like whether or not something is a residue, and like, and if so, and like in either case, like what the advice value for square root should be. So yeah, so once you compute those, we assign them here, right? So is residue gets assigned to 0 or 1 depending on if you know, if like this is residue value is true or false. And then, right, pattern gets assigned to this value from like, right, you know, 2 times the previous pattern plus like, you know, 1 if residue, and then 0 other ones. And then square root gets assigned to the square root witness value we had earlier, right? So, right, so as written, right, like I am doing, like my circuit is like going to assign like correct values to the table, right? So like actually, right, so like the circuit like value. So if I try to look up into the circuit, right, it will only have values that actually match the like output of this function, right? But because I didn't write this this final constraint, right, for the first pattern, the like pattern should start at 0. Like this is actually a soundness bug, right? So it's possible for me to write a different assignment function, right, that doesn't touch any of the constraints, that sort of starts, you know, pattern, let's say, you know, like some like, you know, like 2 to the 128. And then all these constraints would still pass, but the assignment function, right, would be different. And so that's sort of like how you know that you have like a soundness issue in your circuit, right? Is like if like someone else started a different assignment function that still passes all your constraints, but is like actually doing something different in the circuit. Okay, so I think, yeah, so then like, all right, so let's see. Yeah, so like I guess we can just demonstrate this here, right? So like we have this like this test called like test for the pattern circuit, which is just computing, is running the test circuit with 4 values, like 0, like just these 4 values, and then applying the mock prover on it, right? So let's see if we actually, so if we do cargo test, we actually run this, we should see that the test will pass. Okay. All right. So this is the case, right, where we are being an honest prover. But let's say, like, you know, I think if I do, let's say, you know, let's say I do pattern is equal to if I start pattern at 342, then I think, okay, so there's going to be a small pattern problem here because I think it's going to overflow. It's going to overflow because the pattern is too large to now fit into a U64 always. But remember that, like, you know, the U64 is just something that, like, it's not anything that the circuit knows about, right? So like, right, like as long as pattern fits into a field element, then the circuit's going to be okay with that. So I think, let's just say if it makes the, oh, well, so, so yeah, I'm not going to try to like fix this, sort of show it to you now, but like it is possible to, I guess if I make this like FR, yeah, so if I make this like, it is possible to start pattern from a non-zero value here and then still get an assignment function that would pass all of the constraints that I've written because I'm missing that one. Okay, so that's the slightly more exciting example involving quadratic residues. And then I guess the thing that we're all here for is the sort of like the hash functions that are going to be used in the hackathon, right? So So Rohit, who also works for Scroll, has sort of written up these scaffolding files, right? They sort of have like the circuits that you'll need to implement for each of the functions, right? So here, right? So I guess yeah. So like SHA, let's just talk about SHA-2 for instance, right? So here, right? Like you're going to okay. So I guess first we need to talk about something called like the SHA-2 table, right? Which is sort of like an additional thing that we just had in the zkevm that controls how how like the lookups between the various tables are done, right? And so in particular, like the SHA-2 table is going, well, right now it has just one advice column, but you're going to need to add another one here, right? Which has sort of like the digest column. Well, so there's actually a couple things to notice here. It's like you would like to like think like, I just want to do one digest column, right? Which is an advice column. Right. And this will sort of contain the SHA-256 digest for the ID. But it turns out this won't work, right? And why won't this work? Because the digest and the SHA-256 returns is 256 bits. And so that's bigger than the field that we're working in, which only has 200, which you can only safely fit like 253 bits into. And so you actually there's many ways you could like get around this, right? Like you could have like digest high and then digest low, right? So like maybe, digest high is the higher, like the upper one, like 128 bits, and then digest low is the lower 128 bits. And then, to get the actual SHA-256, you would like multiply these, multiply high by, you shift like high over 128 times and then add it on to low. And then so the SHA-2 table just sort of has this construct function, which is going to again, like have the sort of like give you all the columns that you need, the columns, which just sort of returns like the columns in it. And then the annotations, which just sort of has like, here are the names that I want to give the columns. And this is just like a helper function so that when like lookups aren't satisfied between the sub circuits and the EVM circuit, that you get like helpful error messages. And then so like the actual work to do is sort of in this SHA-2 config, the SHA-2 config file or struct. And so here, right, again, there's going to be this configure function, right, in which you're given the table and the constraint system, and you sort of write down all the constraints that you want to hold between the columns. And then this, and then there's this witness struct, right, which is sort of like, here are the inputs to the SHA-2 function, right? So this is going to be a vector of bytes, right? And so like basically every vector of bytes is going to be like sort of like one input to the SHA-2 function that we want to compute the SHA-256 of. Okay, and then, right, so then here are just some test vectors so that you can verify that, you're actually computing correct SHA-256 values. And then here's like the test circuit. Okay, and so I guess like to do the, the final part is sort of like the benchmarking of all of this. And so if you go to the benchmarking, okay, sorry, yeah, I guess first I should just mention if you don't have Rust installed, it's very easy to install. You just find the Rust page, then they have this curl command that you can run. I think that then there's, if you're on Windows, there's a different curl command to run, or there's another command to run. But this should install Rust. Then you go to this repo, you git clone it, and then you just type cargo. So then if you're in the top level directory after clone it, just type cargo build. And then this, well, so I've already built this, so it did not do too much work, but generally it will download all the dependencies, build those, and then sort of build everything until you have built the final output here. So to run the benchmarks, we go to the benchmarking directory. And I just paste this. And so what this command is doing is it's setting the degree to be 10, which is basically just saying like how this is sort of like the maximum size of the trace table that we want to allow. And then, so we're running the tests in the benchmark crate. And then it's important to pass this no capture in, because the default in Rust is that if the test passes, then it swallows all the standard output. And so in this case, the standard output contains useful things like how long each one of these circuits took to run. And so here, right, okay, so this is, all right, so in this case, right, like you can see that, well, you know, the this is for like the this is for like the RIP EMD 160 circuit, right? And so like it just tells you like, okay, this is how long it took to generate the proof and how long it took to verify the proof. The numbers here are sort of meaningless because in fact, like, you know, we haven't written any constraints in the circuit, so you know, there's not too much work to do. So yeah, I guess this sort of concludes like the presentation part of the of this. Are there any questions that people have, or like things they like? Yeah, any questions?
We just had a question about the degree set there.
Yes.
Is that meaning that we're maxing out at 2 to the 10 or 1024 rows?
1024 rows. Yeah.
Great. Can you provide information on the level of resources required to work with halo2-ce and how it performs on an M1 Air?
Yeah, so I'm actually on, well, I guess I'm on an M2 MacBook Air. So yeah, like it doesn't take too many resources. Obviously, like, right, the larger, you know, you can write a circuit that's so large that your the laptop won't like have the RAM to deal with this. But you know, for like, yeah, like I develop on an M2 Air and it hasn't been a problem.
Cool. We got a thank you. I'm just going to remind everyone, if you came to this workshop through the the MOOC hackathon being put on by Berkeley's RDI, they have a Discord, and we have people in there that can, you know, direct questions to our ZK experts on the team from that Discord. And you can also probably find some teams there in that Discord too. Otherwise, if you're not participating in the hackathon, but just want to learn more, you can go to scroll.io and join our Discord and ask questions there. So.
Okay, yeah, so I guess, yeah, that's it. Sounds like there are no more questions. Yeah, yeah, thanks for coming, everyone.
Thanks, everyone. Thanks, Mason. Appreciate it.
Bye-bye.